over to Martin. Thank you.
Cool. All right. Hi, everyone.
Hello.
So yeah, to start off, why did I bother doing this project? Main reason for me was I hadn't done any electronics in about 10 years or so, so I quite fancied picking up a soldering iron again. It was a nice, gentle introduction to it, so that's all good. And second of all, been reading a lot of articles, seen a lot of talks about Scalaz-Stream and HTTP4S. I kind of wanted an opportunity to play around with them, so it was kind of bolted on, even though it doesn't add that much value to a robot. So what the goals for you are, hopefully I'll inspire you to play around a bit with Raspberry Pis, because they are really awesome. If you don't have one, you should get one. Play around with it. Yeah, the Raspberry Pi Zero is £4, really, really small. You can get them really easily. Pass it around if you want to take a look at it. And also to give you a brief introduction to Scalaz-Stream, show you why it's quite a nice model for solving problems. I know not everyone is a Scala programmer in here, so hopefully it'll kind of give you a bit of an introduction to how to model how we model problems in Scala, and hopefully it'll show you a model for dealing with concurrency and processing data, essentially, which might be interesting for any language. So first of all, what's a Raspberry Pi? Didn't really seem complete if it didn't have this side, but it's probably irrelevant. Who's used a Raspberry Pi before? Hands up. Yeah, pretty much everyone. Awesome. So really small, low-powered computer. Doesn't cost much money. As I said, Pi Zeros, £4. Get them very easily. And for robotics and hobby projects, they've got the added benefit that it's really easy to hook them up to things. There's a strip of pins on the top. You can see it on the Pi Zero as well. Called the GPIO. Stands for General Purpose Input Output. It's basically 26 pins that you can control programmatically, and you can hook up sensors to them to read things from the environment or whatever, and you can use them as little electronic switches to control external components, which is what I'm doing with a couple of motors here. So yeah, absolutely perfect for building a robot. Bob uses a Raspberry Pi Model 2B. Let's quick look at the specs. It's got a gig of RAM, it's got a quad-core 900 MHz CPU, and it's got a CSI connector. That means we can attach a camera to the front, and Bob's able to see things. So yeah, fire up a little bit of a demo.
What's CSI?
Sorry?
Crime scene investigation.
Yeah, exactly. It lets you zoom and enhance. Yeah, it's essentially just a connector for cameras. That's all you can do with it. So I'm just turning on now. No. Yeah. So one of the reasons I haven't used a Raspberry Pi Zero for this is Raspberry Pi Zero doesn't have a CSI connector, so you wouldn't be able to hook up a camera in the same way. It would be a little bit more tricky. It's still possible, but yeah. So if we just get Bob on. So what he's doing now is he's creating a Wi-Fi hotspot called Pi-Fi. So I'll get on there. There we go. And now I should be able to SSH onto him. You can see my password, right? Start a couple of things. First one is for the live streaming. Second one is the controller for moving Bob and serving up a web page, which we're about to see. Yeah, man. You're going to be famous, Steph. Alright. So hopefully now... Way! So it's a little tiny camera mounted on the front there. And we've basically got 3 controls. We can move them left, right or forward. You can't do reverse, but yeah. So if we whack him on the floor, go on a little bit of a trip around the room, hopefully. Maybe. Why aren't you moving? Oh. Yeah, there we go. Can we crash into Ben's laptop? Probably. Yeah! Screw Ben's laptop, it sucks. Awesome. Yeah, so that's about what Bob does. So I'll show you a bit now about how he does it, if I can ever stop him. There we go.
This is safety for robots.
Yep.
So how do you think Terminator works? Kill dash 9.
There we go. So, how did that all just work? So when Bob booted up, he's got a little Wi-Fi dongle attached to the USB port. Uses something called host APD, which is a Linux daemon for creating a Wi-Fi access point. He creates his own Wi-Fi access point, and then afterwards I SSH'd onto him and I started a couple of servers. So the architecture of him, we've got two servers. We've got one written in Python. It continually pulls the camera, trying to pull down an image, and it pushes it to any clients that want it over WebSockets. Second one, which I'm going to be talking about today, is a controller server. That's got two purposes. First one is it served out this page, which has some JavaScript which sends commands through HTTP posts. And the second one is it receives these HTTP posts, and using GPIO, it puts the motors in the right states, so he moves around the room, essentially. So how does Bob move? On the front of him, underneath, can you pick him up, Ben? It's alright, he doesn't bite. There's a little ball caster right at the front there.
Ben, can you stand up, please?
Can you model it first, man?
Yeah. So there's a little ball caster on the front. That's just a free ball. It won't have any resistance. It doesn't have any power. It can't move anywhere. But on the back, we've got two DC motors. There's a 5-volt battery, which is your standard like portable battery pack that you use to charge your phone. That powers the Raspberry Pi. There's then a separate battery for the motors, which is a 12-volt battery. That's plugged into a motor controller, which is on the top, and it just slots into GPIO. It allows us to control the two motors just through a GPIO
Pass
pin,
them around there.
essentially.
Yeah?
Pass them around.
On the rampage.
Yeah. So if we want him to move, we put the right DC motor on, he'll move left. We put the left one on, and he'll move right. If we want him to go forward, we whack them both on, and he'll keep on going into Ben's laptop. So now we get on to the Scala part. Platform engineers, the room is locked. You'll leave talking about monads, stroking your functional programming base, and it'll be all good, just embrace it. GPIO pin, as I said, it can be used digitally. What does that mean? It means you can programmatically tell it to be high, which means put out 5 volts of power, or be low, which means don't put out any power. And we've modelled this in Scala by just having a sealed tray called pin state with exactly 2 instances of it, high and low. This is all just standard Scala so far. Second one is a digital output. What is a digital output? It's just something with a function that takes a desired state and returns a task of unit. What's a task of unit? Well, the Scala folk, you probably know more about futures. A task is very similar, but it's a Scala-Z concurrent thing. It's effectively a lazy future. And what does that mean? It's a container, and it's going to produce a value of unit. It's going to have a couple of side effects. That'll be asynchronicity and possible failure, essentially.
So it's a kind of a request for something to happen. It won't necessarily clock into it, but it says actually this will happen at some point.
Exactly. So you can then what's called run it, and it'll have the side effect of making this output enter the state you wished.
Right. Then it'll be entered back up. That's the point.
Yeah. The actual definition of the digital output, I'm using a library called Py4j to do kind of like the JNI stuff, and this is just basically making it a bit more Scala-y, a bit more functional. So it's returning an effectful task where we're just matching and calling high or low on the pin. The controller is the main part of Bob. Bob has 2 digital outputs. It's got a left motor and a right motor. So this is where we're just declaring that. Again, that's implemented in terms of Py4j. We're just saying use GPI pin 7 for the left motor and GPIO pin 1 for the right motor. That's just the way the controller works. So how do we said that you can move in 3 possible directions and not move at all. How do we express that? Well, this is an action. What is it? It's a function of a controller. A controller is just 2 motors, a left motor and a right motor, and it produces another task of unit and takes a couple of states, 1 state for the left motor, 1 state for the right motor, and the side effect that this task has is it causes the corresponding motor to enter the corresponding state. So from that, because we've got 2 pin states, we can have exactly 4 actions out of it. We've got forward, in which both motors are high. We've got halt, in which they're both low. And then in between, we've got left and right, in which he moves left and right. Okay?
So you're abstracting the kind of the logical what you want to do from the actual implementation of how it actually does it.
Exactly, yeah. So actually running the action, as I said before here, it's just a function of a controller to an effectful unit. So here we just apply the action to a given controller. It's curried, we'll get into why later. And that's essentially it for the Scala modelling of the problem part. Now we come into the Scalaz-Stream part. So people familiar with Scala, that kind of makes sense, the way those things were modelled.
Yeah.
Cool, I'm seeing some nods, which is always good.
What does current mean for those who don't know?
So essentially,
We've been stopped doing Scala for like 6 months.
essentially this is a function, but it's got multiple parameter lists, and I can apply this by just providing this parameter list, and it will give me a function of an action to a task of unit. That'll be important later, and we'll get more into that. So now, Scalaz-Stream. What is it? Streaming input-output library for Scala. Why did I choose to use it? Mainly just because I said before I was interested in it and seemed like a fun thing to play around with. It's soon going to be replaced by a library called FS2, which stands for Functional Streams for Scala, because some people fell out in the chat room. There's always a few rifts in the Scala community. This is a pretty big one. A lot of projects are affected by it, including Scalaz-Stream. I'm not using FS2 with this because the other library I'll talk about briefly is HB4S. That hasn't adopted FS2 yet. It's politics, man. So the important thing is the concept will be the exact same thing, so it's transferable. So the main thing in Scalaz-Stream you would think would be a stream, but it's actually a process for some reason. And what is that? It's just a possibly infinite stream of data of a given type. It can be a finite stream, it can be an infinite stream, it depends on what you're trying to model. Data is always pulled from a source. Pull is very important there. Sources don't push, they get pulled from. And essentially produce something that produces data. It can then be sliced and diced in the usual functional manners, so your filters, your maps, your collects, everything that you would expect. And eventually the data is then piped to a sink. A sink is just something that consumes data. So it could be a database, it could be sending an email, it could be writing to a file, or in this case it's controlling GPIO. Some effects such as asynchronicity and any other effect you want to use can be accounted on the way. And the really important thing about Scalaz-Stream is a stream is inherently sequential. So only one piece of data will flow through the stream at a time, and the bottleneck will be your sink. So your sink is constantly trying to pull from the source, have its effect, store its database record, enter its state on motors, and that is the bottleneck essentially. You're not going to get any concurrency by default. You have to explicitly ask for it. So I just talked about what a process is, how do you declare it. It looks a bit scary, but it's not really. It's got 2 type arguments. The first one is some container. With Scalaz-Stream, you almost always use task. Sometimes you use nothing when you don't want to have an effect, but I've never seen anyone use anything other than task. And second one is A, which is completely unconstrained, and it's just the type of data you're working with. That can be whatever you like. So how do we make a source? This is a pretty standard function. It's called readLine. It returns a task of string, so it's going to be an asynchronous produce string that might fail in the creation, and all I'm doing is I'm reading from standard input. That's just a normal Scala function, nothing special about it. I can turn that into a finite stream with exactly one piece of data in, which is a string, by saying process eval read line. That's going to evaluate that function exactly once. It'll then say, right, source is over. I can turn it into an infinite one by saying repeat eval read line, in which case it's going to try and read that line as much as you ask it to, essentially. As much as you pull from it, it'll try to read. It's never going to be exhausted.
Will it block if there's a thing to read from it? If it is like reading from like standard in or something?
Yeah, so it won't block per se.
It's asynchronous.
Yeah, it is asynchronous, but yeah, it's not going to be pulled from again until the first pull finishes, if you see what I mean. Yep. So a sync, the type signature looks even more overbearing, but again, it kind of matches how you would naturally do it in Scala anyway. So this is a sync, and it's just a made-up one for sending an email, and in this, it's going to take in an email address that you want to send to, and it's going to give us back a task, and the side effect is going to be to send an email. In this case, I'm actually just writing standard out, but you could use whatever library you want to send an email in this case. And I can lift that into a sync pretty easily by just partially applying this function, so not providing an address, and saying that this is a stream of functions from strings to task of unit. That's all this is saying. This is saying that our data type is always going to be some unconstrained type to a unit wrapped in whatever container you want to use. That's all it's saying, essentially. Hopefully that's pretty natural and not too much boilerplate. So we had our interpret function earlier, which I said we could partially apply. That's absolutely perfect for turning into a sync. We can give it a controller. We can not provide a second argument list, which gives us a function of action to task of unit that fits the type signature of a sync absolutely perfectly. We can say repeat eval, because this is going to be an infinite sync. We can take however many of these actions we want. We're never going to give up trying to consume these, essentially. How do we declare a source? So this kind of brings us into a little bit of a side point. I mentioned earlier that it's inherently sequential and sources will be pulled from. So you might say, well, what happens if you've got a really fast source which is producing a lot of data very quickly, something like reading lines from a file? And what if your sync is really slow? What if it's a legacy system that you're trying to do a HTTP post to or something like that? Like, what happens there? You're going to block your source? The answer is no, not if you want to. There's an async object, and it's got lots of nice data structures that work really well with streams. So here we say, I'm going to have a bounded queue of 10 of my data type of action. The source can produce as quickly as they want, and as long as there's no more than 10 outstanding pieces of data for the sync to pull down, I'm not going to put any back pressure on the source to slow it down. But as soon as there's 10 things waiting for the sync to consume, it's going to apply back pressure, and that's essentially how you can control different speeds of different sources and syncs. But yeah, in our case, we're just saying I want a bounded queue of actions, and I want that to be a stream. This is saying turn this into a source by just continually trying to pull something from the queue. So if we whack this all together, this is just the code from the previous slides on our interpret function, our source, which is just our queue, and our sync, which is our interpreter. All we do is we say source to sync .run. The .run is a bit unnatural. The first .run says compile this into one task, one stream. You'll get back a task from it. We then run the task, and yeah, we get that. So yeah, whenever something is whacked on our actions queue, the sync's going to try and pull it down, and Bob will move, basically. So that bears the question, we've got this running, but nothing's ever going to appear on the actions queue. How do we do that? Bob does it by starting up a HTTP server and every time you post to a certain endpoint, it will put a certain action on the queue. So this is where HTTP4S comes in. It's a really lightweight library, and it works brilliantly with streams. You can essentially say HTTP service is just a partial function of a request to an asynchronous response, essentially. And here all we do is we say, when you post to root/left, whack on the left onto the queue, and so on and so forth for all the other types of actions. So that's our HTTP service defined. How do we start it? As I said before, it works really well with streams. All we do is we say, listen on port 8080 on all interfaces, mount the service, start it. That gives us a task of unit. We lift that into a stream by just saying eval, because we only want to start exactly one server, and that's not going to, that source won't finish with that data item until the server is terminated for whatever reason, essentially. So we've now got in a state where we've got two processes. We've got one that listens to an in-memory queue and tries to set GPIO to the right state, and we've got another one that starts a server and tries to whack things on an in-memory queue. And I kind of said that both of these processes are entirely sequential, and they're both infinite as well. So we're always going to keep trying to pull from the queue, and we're always going to keep trying to listen for HTTP post requests. So we've got working with two infinite queues here. If we try to just run them both, this one's going to be fine, it's going to keep on waiting, but we'll never get to this line, so we're never going to have our server, never going to have any input to our queue. So how do we get around that? As I said before, you've got to explicitly ask if you want concurrency. So we essentially just say merge to them both, and we say, right, these streams are okay to run in parallel, and this produces a new stream, and we can just run that, and it'll do both things. So that's essentially the main part of the presentation. I'm just going to end with a couple of notes about it. So hopefully you can see that Scalaz-Stream has given us a pretty nice way to deal with processing of data, essentially. There wasn't much boilerplate. It was just standard Scala, essentially, apart from a couple of process evals and stuff like that. And yeah, it's got a good benefit that makes testing really, really natural. So before I define a trait of controller, which has a left and a right motor, I can easily make a stub one for testing by just having two mutable seeks, and whenever the left motor is asked to enter a certain state, it'll whack on the state it was asked to enter onto the left motor seek, and so on and so forth for the right motor one. I can then easily pull that into a test, so I can kind of tap into the stream at the part of the interpreter talking to the GPIO, actually have it talk to the stub controller, and rather than starting up a HTTP server and filling up an in-memory queue, I can just say use this stream instead. It's a finite one, it's only got two actions in it, and this is going to run very quickly because this input's going to be exhausted very quickly, and then we can check we're in the right state afterwards, essentially. So yeah, that's pretty much all from me. Hopefully I've shown you a bit of Raspberry Pis and how you can play around with them and hook them up to stuff, and kind of inspire you a bit to get out there and make something. And yeah, hopefully I've shown you why Scalaz-Stream's quite a nice model, and yeah, same again, hope you can be inspired to play around with it a bit. Cool.
Time for some questions.
Yeah. Mr. Lee?
How long do you think Bob would last in Robot Wars?
I don't know, I'm yet to attach like a laser or a flamethrower to him, but I don't know, maybe. Yeah, Robot Wars robots are pretty huge, they're like that big, so maybe he could just get out of the way of them pretty quickly. I don't know.
Can both move both forward and left? Perform two actions at the same time?
No, he can't, no. No, because he's only got two motors.
The motors are not variable speed, so you
No.
couldn't do on the rise a bit more speed, so it goes like that.
No, unfortunately not. The motor controller supports one variable speed output, which isn't much use. Yeah, it's just a limitation of the motor controller. You can get more expensive ones, it would be able to. Mr. Tom?
In terms of duration of movement, how do you know how to keep, well, how long to keep the state high when you move forward? Is it, because obviously a post is a single point in time to this action?
Right, okay, so this front end thing here, it's a little bit of JavaScript. It's listening on key down, so when I put this key down, it's going to tell it to go forward, and as soon as I let go of that key, it's going to send a halt and tell it to stop.
I see.
There's a little bit of a complication.
I see.
There's a little bit of a complication in that because it's going over Wi-Fi. If you're holding forward down and suddenly he goes so far that it's out of Wi-Fi range, he's going to keep going. So so I've got some. I didn't show it on here, but I used another Scalaz concurrency structure called Signal, which basically allows us to have a heartbeat, and this client checks in every 200 milliseconds. If it misses check-ins for about 2 seconds, he just stops.
I suppose you could do like a hand dryer in a toilet where there's a maximum time, even if you've got movement after a certain time, it assumes there's something funny and kicks off after a minute.
Exactly. Yeah. That might have been after he fell down the stairs. I invented that.
Great.
Yeah.
What's next for Bob? Do you have any plans for further enhancements?
I'm kind of torn. Part of me wants to buy some sensors, like an ultrasonic one, so we can detect walls and move for himself. Other part of me wants to play around with something like OpenCV and do some vision stuff and have him follow people or something like that. That's a bit creepy, but yeah.
Does the camera, this model supports only JPEG images, or it can support live stream as well?
You can live stream of it properly. All the tutorials on the internet tell you to run VLC as a server and have a browser plugin of VLC, which seemed a bit horrible. It seemed a bit 90s, and I couldn't get it to work without a 5-second lag, so it was a bit useless. Yeah.
So is that just a constant set of JPEG images getting refreshed?
Yeah. So there's a little Python script which basically pulls an image, JPEG, from the camera. It'll basics for encoder, and it'll whack it out on a WebSocket to anyone who's listening. The client here takes that, decodes it, and just whacks it as the data of an ing element, essentially.
Could you do that in Scala?
Could have. Yeah, could have. So HTTP4S doesn't have good WebSocket support, and I kind of wanted to just get it done quickly, but yeah, I could have.
Anything else, man?
Anyone else?
Good stuff. Thank you, Martin.
Cool. Cheers.
So it's, my talk is Devops tooling on the go, pun intended, go as in Golang. Let's see first a bit about what Devops is, in case someone in the audience doesn't know.
Not again.
Yeah, well, it's a paradigm where you, the classic way of doing things in a software house would be you had the developers developing the software or the service, and then you have the ops person who would take the artifact or not, or whatever output the developers would give him, and some instructions to set it up and deploy it to production. So there were two separate functions. The collaboration was kept to a minimum. The DevOps paradigm is like it's like bringing down those silos, having people from both the dev team and the ops team working together in tandem, trying to apply the good things from both paradigms into the new paradigm that's called DevOps. And that's a lot of that has to do with applying the software patterns that the developers were using in the doing operations. And that helps a lot with automating everything you might need to do, from deployment to, I don't know, bringing up infrastructure. So what provides the benefits of DevOps is infrastructure as code. You could describe the whole infrastructure from networking to the servers you want as code, instead of having to go and create the infrastructure you need or rack it up like in the old days in your data center. You get automated delivery pipelines You get better control of changes because you, following the software paradigm, you have source control, so you can see what happens, who did what. You can have collaboration, and of course you can get repeatable and reliable operations. You do it once this way, you can repeat it and get the same results, the same expected results. And of course the collaboration and sharing of knowledge is way easier. Especially if you use something like GitHub, you can have peer reviews on every pull request. Someone can go and see what you did and how you did it, and it's very easy to benefit from it. But Devops comes with some requirements. You need the proper tooling to be able to accomplish all that. You're pretty much as good as your tooling. And in the open source wilderness, there are lots of tools. Some of them are good enough and accomplish what you need. But sometimes you won't find what exactly you need. So you will end up having to write your own tools. So you have to resort to custom tooling. And there are some requirements that you need from those tools, usually because, for example, you need to be able to run your tools into different platforms. You may work on a Mac OS X environment, but your server may be Linux or even Windows, if you have that in your organization, like we do. You want them to be low footprint. You don't want your tooling to consume the resources that the actual service was going to use. You want to be very easy to deploy and effortless. Otherwise, if it takes you, if it's like deploying your service just to deploy your tool, then you have failed. It's an issue. Low upkeep, of course, to be easy to modify, change it to do what you need to do. And if it's easy for someone to understand what it does, but just by reading the code, it's very beneficial because if someone comes onto your team and can easily understand your tooling and how you work and why. And of course extend the functionality to get new feature scenes, new ideas. So I recently discovered, in the sense that I started using the Go language. That came out of Google, which is, as it says, a highly opinionated, statically typed language. It was developed in Google because they were facing the issue of having big projects with big teams. They were writing in C++, I think, that because of the performance they required, it was C++ was providing that performance. But it was very hard to start using it, especially if you were going into a new project or you were getting more team members or teams collaborating with each other on a big project. They had a very hard time to get people started on the project to be able to produce and start working on it. They would first have to learn how everything is set up, how this team was doing things. And they were very frustrated with that, so they decided to design a new language that was offering performance and what they needed and easy to just get working with it. What are the features of Golang? It's a true platform, true cross-platform and cross-architecture language. It supports all those platforms. And some more that I didn't even include, and all those architectures. So we could easily run Go in Martin's Raspberry Pi because you can just yeah, with a lower footprint on the JVM. Shots fired.
Say more on.
Yeah. So as I said, highly opinionated, enabling easy understanding of code and productivity. For example, you even have to have the block brackets starting on the same line, not in a new line. Otherwise, it won't compile. It will refuse to compile because they didn't want to see different styles from different developers. They just wanted something that's easy to read, and it's just that.
Sorry,
no arguing nothing.
it's an inbuilt formatter, isn't it? Actually
Yes,
in
yes.
language, so you can't.
Yes, that's to fix your transgressions because it won't compile otherwise. So they provide you with the tool to do that. Unused imports and variables are not allowed. Doesn't compile again. You will complain. It's a simple C-like code structure. Most people are familiar with it. No obscure things like Scala.
That's different to simple.
Yeah. Well, package system with an implicit structure. This means that you don't have to specify a lot of metadata anywhere. Nothing. Just the structure. You know what exactly the packets include. It's implicit. It's not object-oriented because they felt that abstraction is an issue, and object-oriented advocates a lot of abstraction. They kept some good things from object-orientation, but it's not object-oriented. Easy dev environment to set it up and start writing code right away. You just get going. I think that's why they called it Go as well. You just go. And you have a single tool that does everything for you, from testing to linting to compiling to debugging. You don't have multiple tools, extensions, extra tools to do your job. Just a single binary. Continuing with the features, it's, as I said, it's statically linked. This means that it's very easy to package and deploy. You can just drop the binaries on your platform, or package it up with other things. As a user deployer, you don't have to worry about any dependencies or versions of software. If it's compiled for your platform, it will just work there. You don't have to worry or care about anything else. And of course, works out of the box because it's a binary. You just run it. Then it's very performant. It achieves C-like level of performance. It has concurrency built in, and it's not something that was an afterthought. Concurrency is actually a way to structure your code in Go. And of course, you get performance benefits out of it when possible, like when your system has many threads, then you can run things in parallel. It has a garbage collector, but it's compared to the JVM, it's extremely good. You get guarantees less than 10 millisecond stop the world events, and they're very rare. I haven't seen one in what I'm doing up to now. As I said, concurrency is at its heart with native threading primitives. It's very easy to use. They're called Go routines, and you have the channels, which is a way to communicate between your routines, to exchange data or whatever you want to exchange. They're getting multiplexed into system threads transparently. It's all managed by Go for you. And as I said, it allows for parallelism when the system you run it on has that ability. And you get expected behavior out of it, regardless if it will run in parallel or not. So now we will have a demo. I will demonstrate how easy it is to get started with Go and do some simple things. So first I will go to the website. It's this one. You can download your archive or your package. I prefer the archive because it's pretty much standalone. So you just download it, extract it, and you get working. You don't have to install it in your system. You can just delete it and be done with it if you don't want it anymore. It has no system dependencies or installing anything else. So the only two things that we need to set now to get started, it's two paths. The Go root, which is where the Go binary is situated with everything, which is just the directory just extracted. And the Go path, which is the root of your workspace. And I will create that workspace right now. You just need 3 directories to get started: bin, package, and SRC. Yeah?
Would you mind increasing the font size?
Excuse me?
Font size is up.
Yeah, of course. Oops.
You get your opera glasses here.
Just thinking.
Doesn't remember the Zoom thing.
Come on,
Oh, okay.
There we go.
So yeah. So now one more directory just to structure my code. It is highly suggested to go like that, github.com and your account. So as you can see, this is the workspace. Is it visible from the back? No?
Yes.
I don't think I can make this bigger.
You got the source up here.
But yeah, the source is gonna be.
Just do tree in the command line. Just do tree in the command line.
Okay.
So the files is Oh,
Yeah, it's Mac OS X. Yeah,
Find document.
yeah, but I can do that.
They are.
It's just that. So I will create a subdirectory which will be the name of my project. I will name it AWS example. And here I will create the main file of any Go program. It's main.go. And in the interest of time, I will include another file that I already have written before. It's nothing special. It's just AWS SDK calls. As you will see here, it's just like get 3 functions. Very simple things: get instance, get volumes, get snapshots. It's just taken out from the AWS official SDK recommendation. It's nothing special. I will now compile my program. As I mentioned, you have a single Go tool that you can do everything with, and it's called Go. So as you can see, I got an error because I don't have the dependencies I need, and that's the AWS SDK because I just started my workspace, and I can get it as simple as that. Go get and the GitHub URL or whatever URL the dependency is on. It will get downloaded in my workspace, not in the system. It's self-contained.
Just to note also, that's going to install in your Go path, isn't it? Not
In the Go path, the Go path is the root of my
your current
workspace.
directory,
Yeah. And another one that's coming from the AWS Go SDK.
Is that just pulling the latest master? Or will that start?
Yes, but you can also get versions if you want specific ones tagged. but there's no reason not to get the latest with AWS because their API is backwards compatible and it should always work. At least that's their idea.
Yeah.
So now I will run go install, and it's compiling to binary, and it's done. And because I have in my path the binary folder of my workspace, I can run directly like binary. And what it did, it went into the playground account that we have in AWS, got the instances, the EBS volumes, and the snapshots there, and printed their IDs. Very simple. Now let's, that happened sequentially, but those things are separated, like the EC2 instances are a separate request, as you saw, the EBS volumes are a separate request, and the snapshots are a separate request. I could do them concurrently and save time, get the results faster. There's no reason not to. In Go, having concurrency with Go routines is as simple as doing that. Just add in front of the function call, method call, or whatever, the keyword Go. And because those will run asynchronously and they will not block, I need to block it myself in the main for now. And import my first package.
Is that because the main function would have exited before we did it?
Yes, exactly, because the routine would run asynchronously and the main would end and you won't get anything. That import is from the built-in Go library. It's called time and provides the sleep function. So I will compile again.
How big is the binary crates for such a small program?
Probably it's gonna be something like 11 megabytes, but it's all included. It's but it doesn't change much. Even if you do a lot more things in there, it will still stay around that size. So it's like, yep, it's about 12 megabytes. So I will run it again. As you will see, I got the results faster. It didn't end because I have the sleep. And every time I run it, I may get them in a different order. For example, now I got the instances last because the request completed last. So they run concurrently and probably in parallel based on the threads I have in my system. Let's see if I wanted to have some communication to know when its function ended its work, and I know that I can then exit the main program instead of adding a random sleep, because let's say that I didn't know how long it could take. It could take from 5 seconds to a minute for some reason. As I mentioned, Go routines go hand in hand with channels, which is a very easy way to communicate between Go routines. And I can do something simple like I will make a channel now. Pass it on to the routines, to the functions, which are routines as well. And of course I have to modify them to accept the channel. As you can see, channels have types. They can be from any simple type to any complicated structure.
Is channel a keyword?
Yes, it is. So every channel is like, you say that C1 is a channel and is of type id. So the most simple thing I could do, have the functions return something to the channel once they're done at the end. So I will have them return the id01. And here, I will get that data from the channel. This will block until I get input from the channel from any of the functions. Sorry, it's actually and I'll add to that variable, which will actually, it's actually a counter to know when all the expected amount of functions, Go routines have completed. So I can add the symbol if. I break the for loop. And let's compile. As I said, if you don't use something, it will complain and it won't compile.
Why is the file here instead of in the root of the project?
This is the root of the project. AWS example. All the other things are my workspace. I can have multiple projects at any time.
Okay, manage multiple versions of projects. So could you
Yes.
have different versions of AWS within that?
Yes, I could. There's a way, it's called Go packaging, where you can actually specify the tag or the release version on GitHub or any source control, and it will fetch you that. So now we should get the request, and it takes it right away the moment it's done.
And the source directories are all shared libraries or generally as well, like the AWS tools.
Yeah, the AWS one and the other one that they downloaded, they're in here, as you can see, in the source directory. That's why I said that everything is self-contained, from the dependencies to binaries to everything. I can just delete the Go example directory and everything's gone. Nothing will be left on my system. Or I can just pick it up and get it to another system.
Very cool.
And of course, one of the good features of Go, as I said, is true cross-platform. I could build my binary, my program for, let's say, Windows. All I have to do is that.
What's the difference between build and install?
Install is the same as build, but it also installs the binary into your bin folder. So you can easily run it right away if you have it in your path. So I have my bin folder in the path, and I can execute it.
/bin or something.
Yeah, I could, but it's easier that way. So, if, as you will see, there's an exe in here, and it's not just a file name. It's a Windows executable. Now, if I pick that and put it in the Windows machine, it will just run. Just that binary. I don't need anything else. And do we have any time left?
I've got some questions. I think we have at the out.
Yeah, well, I don't know if it's good to solve the other tools I wrote in Go. If there's any benefit in showcasing the other tools I wrote in Go.
We can kind of share them around onto the
Yeah.
mailing list after.
Yeah, of course.
A couple of questions for anyone?
So, questions, guys?
In your shared library functions there, there's a bit of boilerplate through the top of each function. Is that just you didn't have time to extract them, or?
Which one?
In your other, your functions file.
This, AWS.go.
Yeah, the AWS config blocks that's boilerplate
Yeah,
on top.
yeah. It's just for simplicity.
Okay.
I literally picked up the examples from the documentation. I didn't do anything special.
Okay.
But yes, I can make them better. I have made them better in my other tools.
I think you mentioned a lot of benefits. Have you come across any kind of drawbacks whilst working this?
I don't know. I haven't seen any issues up to now. I was very impressed with how easy it is to pick it up and start working and being productive right away. That's why I did this presentation, to showcase how easy it is to start your environment and just get going without having to do anything special. And I even had the pleasure of trying to extend Terraform this week after a suggestion from Tom to add a new resource for AWS that wasn't there. And it took me less than a day to read the Terraform project that has zero documentation about how it's structured or how it's done. And it's a very big project. If you go to the GitHub, GitHub has Terraform, you will see it's like massive. And it took me less than half a day to understand how they do things and to extend functionality there. I was impressed by that. With any other language that has a massive project, you will be like looking around trying to see what's going on, the over abstraction of everything and all those things. So I believe that Go accomplishes the things that it set out to accomplish.
Great. Thank you very much, Ilias. That's fantastic.